Hello, good evening.
Evening. Can you hear me?
Yeah,
Is my screen visible? Is it?
Yes, we can see your screen.
Yes, great, thank you. How many participants roughly are expected?
Let's wait up to 30 probably. Usually it's around 30, 40.
just a screen flash input provides shorter form for user.
Okay, there are about 31 of us plus the ones, something like almost 40. Shall we start? I guess so. Good evening. How are you all doing? There is an unmute button in your MS Teams. Yes, or you can react with highs about welcome activity gladly. Great, you are alive. So today I will be talking about Tagless final, which is a programming technique which I will explain in the next details, next slides. My name is Reit Svenbachs. I have been programming Scala for something like 2 years, and I've been programming before that. And welcome to the Tagless final lecture of Evolution Gaming Scala Bootcamp. So I saw that in the schedule you can you had like algebraic data types, you had implicits, you had some cats already. So I assume you are up to speed. Perhaps not all of you, but at least some of you are quite up to speed with that. So this first slide is already using that information and knowledge. So I have a question, which I had when I was reading the documents to prepare for this presentation. So do you see this array? Is this data or is this code? So obviously this is data, but what if we wrote it instead like this? This is code, right? And so after reading the materials that I had, basically this is this whole lecture is taken from the lecture notes of this research paper by Oleg Kiselyov. And after reading it, I realized that the boundaries and distinctions between code and data are a bit more similar. The boundary is less precise than I used to think. So another example is this right here. Is this a code or data? So the previous example, this seems like data, and this seems like code, but actually they are quite similar. They can both be both. So if we instead write it, what do I have here? No, sorry. I will just mute my Slack, otherwise I will be disturbed for error. If you have something related to this presentation, I won't be reading Slack. You just unmute yourself and please talk. So yeah, if you draw this instead, so the abstract syntax tree, then it can be code. And this is something that we have to realize and notice in our code before we can actually get any useful insights from what Tagless final is and what it all means. So this was a thing that I was confusing for me when I was first reading the lecture notes, because I was looking at the 8, 3, and 4 and thought that might be the data that we're actually kind of talking, but actually the Tagless final is about the expressions. So maybe that was obvious for you if you know anything about this, but it wasn't for me. So I would these slides are to clarify this right up front. Okay.
Excuse me,
So
may I ask?
Yes.
Good evening, first of all. The previous slide with arrays, is it a Scala syntax or is some pseudocode or abstract language? Is it Scala?
This is not Scala. This
Okay, thank
is
you.
also.
Looks like Python.
Sorry, yeah, it's not Scala, but
Yeah,
it can be.
you.
Yeah, I'm very sorry. I would have liked to do it in Scala, but I just know. I know quite a few languages and I got lost. I'm sorry. Yeah, but this is pseudocode. I assume you can translate it to Scala, so it would look like And the other one would be obviously,
Yes, I
and
got
so
it.
on.
Thank you. Thank you. Thank you.
Yes, yes. Okay, and I had a minor note, which is I wrote this presentation sort of for me, so I'm coming from to it from my end. I hope it will also be interesting for you. At least I tried. Um, so if we make an algebraic data type that represents this expression, then we have the data for the code that denotifies this. So algebraic data types are data themselves, but if you look at them as like syntax trees of expressions, then actually the expressions of data have the meaning of code. Yeah, so Tagless Final talks about ADTs, but with the interpretation of looking at them as code, which is more interesting for us because we're programmers. So the specific interpretation of that. So when we say we use ADTs to compute something, we can also say that we're interpreting syntax trees, and yeah, so you can either say you are computing. I think I'm going to repeat myself, but yeah, folding ADTs is the same as interpreting code. And if you will read this paper later on, which is not so easy to read, but if you will, then that is something that will be there. We'll get to like simpler examples which are less abstract, but I felt that this intro might be useful. So, and let's move on. So let's get to a concrete example where we further develop this idea. So we have this code, and it computes to 9, obviously. But what if I told you we can also compute it differently? We can, with the same idea, we can make a string. Like a computer has the number 8, which is not a string internally. It's made up of zeros and ones, but you can make a string out of it, right? Right. So you can pretty print this code. Yeah, this expression. You can write it in a way that would make the string. You can also make a program that turns each number into something that represents the number but is not the number itself. For example, a list of units or a list of some things. So any number can be represented as a list of n. So 3 can be represented by a list of 3 things, of 3 ones, for example, and so on, which is something they do in mathematics in like set theory. Or you can do like, you can combine computing the number itself and the pretty printing. Or you can do all 3 together. So example, if you want, if you have some expression that you keep on computing, and and it's being computed for a long time, then you might at any point want to get the result, or you might want to get the pretty version of that code. So you would then store both. But the expression that computes the result would have to have the same code because you don't really care about the details. So this is a way, Tagless Final is a way to make, to abstract in a way that lets us speak the language without caring about the precise interpretation, which we can later on specify. Does this make any sense? I would usually interpret silence as a big no. But we will get to code, maybe then it will make slightly more sense. All right. Anyone? Does it make? Okay, I will go on. Maybe it will start making more sense. So the thing that is common amongst all these 4 examples is the fact that we're combining things. So we're talking about the pluses, the minuses, and the numbers. So if we talk about data that can do all these things, so we don't use the actual code, we just talk about data that represents these things. Then if we make that into a trait, then we get a trait. I will show you this exact trait without pseudocode, like in just a moment. Then we have like 3 things that we need. We need to make, we need some representation of the thing we're computing. So it's either something internal with, so the examples are like we're making a list of things, or we're building a string to represent the pretty thing, or we're just using the numbers themselves. So we need to make get a thing in the data type that represents a number. So this would be this interface. The wrapper is some data type. Like imagine this could be an int itself. Again, we are always, if we were building a theory, mathematical, then which is generalized. Then it's good to keep in mind the examples, and to the examples you get to understand it truly. So yeah, this is the ints, the strings for pretty printing, or the lists of things. And so if we let's think about the int list analogy. If we have 8, then this would be a list of let's say ints, which are like 1. So 3 would be represented by this. So this is the method. This is the method that would create the number in our domain. So it's an embedding, like from one set to another, from one type to another. Then we can also negate. This is the negation part. And we can add 2 things. And if we have that, then we can write one code to compute this with all of the interpretations. But depending on how we write it, there can be a problem, which is called the expression problem. If you notice, I haven't explained the title of this very slide. Very uneducational of me, but still. The problem that may arise is that depending on how we write code to denote this thing, we may or may not break the code that interprets it in a different way. So yeah, we're talking about data, and we interpret it like we compute it. And if we add more features to the expressions that can be there, we may also break the interpreters. This is the practical uses. Okay, now we go to actual code. I do have it open. Right, I will think about just a second. This is a quite abstract topic, so we will just take a look at numbers, but so kind of what we're really doing is this. If we're making code as data, then we're basically making another small programming language in our own language to make it. Yeah, well, we need to do that if we want to like do all these 4 different things based on this expression. Then we have to kind of make a programming language in our programming language to make sure that that really works in a statically typed language. Well, I think it's a mouthful, and that's why I'm sorry. It's not immediately so intuitive to get this, because like this is quite a difficult topic, and I'm haven't battle tested this in, presentation a number of times, but let's go to examples, then it might make more sense and be practical. And also,
can I ask a question? So we break down domain in algebras and define an interpreters that converts our algebras into the meaningful operations. Yes, if I understand you correctly.
That sounds about right, yeah.
So,
Yes.
so we need to somehow describe the way we make some calculation. For example, for this example, and we need to write an implementation for some abstract way of managing this operation. Yep.
That sounds about right, yeah.
For every type, we want to apply these operations.
Yeah, correct. And so another way of saying that is that we are defining an algebra. So this is an algebraic operation, which is this kind of the same as writing code. And for any set, so we're describing an abstract a trait, scala trait that represents an algebraic structure abstractly without any tying it to any concrete one. So there are both mathematical and like programming type ways at looking at this. And what you both said, that makes sense. And I hope I haven't confused you with like switching between the ways of talking about it, but we will have code that will, I don't have a lot of slides. It's the last slide, and then I have like final notes about the practical uses and references. I don't even have a thank you slide. Okay, so, and just to mention again, the expression problem is the fact that depending on how we encode the either data or the same way around text the code, depending on how we will encode it, we will break the interpreters or not. Enough with the slides. Okay, the first way to do it is
could you please increase font size? It's really, really tiny.
Bigger, smaller?
A bit more, please.
Yeah, or maybe on a full screen, like because it's.
Do we need the right part?
Yeah.
We don't need it.
Not immediately, no. So yeah.
Thank you.
Now it's better. Thank you a lot.
Thank you.
Thank you for the mentioning. So yeah, the expression problem is the fact that we'll break the interpreters. The way to solve it, as proposed by the paper that I'm basing this lecture on, and which coined the name Tagless final, is to make the interpreters final, which I will explain, and tagless, which I will not delve into. So if we do it that way, we solve the problem. And also I wanted to mention the paper says that there's a bunch of research in programming languages that showed how it was developed over time, and they did not arrive at this conclusion immediately, which is kind of surprising, because in hindsight, this seems like obviously very simple to do, but programming languages developed slowly. We didn't always have Scala. So if we're looking at the solutions, then it's like, so what? Yeah, well, this is obviously very easy. So keep that in mind when we look at the actual code. At least that for me is like something to think about. It gives me like an awe of the topic, certainly. So here we have the same number example, and we have the initial encoding here, and we have the final encoding later. And they're shown to be kind of the same way of doing the things. And so this is our set, which will contain all the expressions. So we are not abstractly defining some set that will have the operations where we have only one set which will have all the correct expressions available. So we can store a constant which holds an integer. We can negate that expression, so it can contain internally either an adding expression or a negation expression or the constant itself. So it's referring to itself. And we can add things which also refer to the big set which can contain the smaller things. I hope that makes sense. It should. And we can write, this is wrong. This is the this is the way we write it down. So we're adding two things. If we count up the parentheses, we're counting up two things. One is the -3, another is 4. And if you're thinking, well, this is not the same because it looks different. Well, that's kind of true, but the internal structure of it is the same, and that is the point that we yeah, if we just would first of all, the first difference, this is like a minor detour, but if we write it in a way, like imagine if the const was like this print symbol, if we add as instead of plus we write an add. So basically it's okay, I'll write it a different way. If we have this expression, so we call it, we rename the minus into an egg, and we rename the plus into an add, and the other add. And then we swap them in so this is the notation that is called infix. So it's like infix is this one thing plus another. And there's also the prefix notation, I think it's called that, which is plus one another. So this is what we're doing here really. So it's just renaming and moving things, but the internal structure would be the same. So just finish my point, it's this. We did this once, we changed the notation again, and we arrived to this from this to that. Here, well, I have removed the constant thing here and here and here, but I hope you know that it should be there. So the structure is the same, it looks a bit different, but it represents the same expression. I hope this was useful to you, and I didn't even think about it when I was creating this thing. So, all right, we have our expression, we have all the correct formulas inside of it because they're composed of the correct structure. And now we are ready to evaluate it. So one way is to actually just compute it with numbers. This is the same. We turn the constant into the same number. So one step by step. We have an expression. If it's one of these, then we compute it to a number. If it contains a sub-expression, then we turn the sub. So these two are expressions. Then we evaluate those two numbers, and then we sum them. And so if we destroy them like that, destruct them like that, we'll get an integer. Well, this is like very uneventful because we could already do that. But the good thing is that we can turn the same expression without, see, we don't have, there's no interpretation, it's just a syntax tree. The data that makes up this expression. Okay, we can reuse it without, so we don't show implementation details here. We can reuse it to make a string. So that's the cool part. And that's very nice. Like we can, as in mathematics, like, where did I stop? Okay, I'll finish the thought later on. But yeah, we can change it into a string. And we can try it out. And in a bit, I will show you where the problems start beginning. This is the initial way of encoding expressions. And so if we run this, this is Numbers.scala. So where is our main function? What, have I lost it? No. I will just copy this line over. Oh, in the code, I will, in the SBT, I will print this, the expression itself. Oops. Oh, the evaluated version and the show version. So it will say initial in front. So let's try it out. 4. So yeah, the expression itself, the number, and the pretty printed version. All well. So that is nice. But okay, what if we add another expression? We have expressions of numbers and some summation and negation. What if we know that languages can also have like another operation, for example, multiplication. So if we add this, obviously we have to fix these two because it destructs the expressions that are called expression, and so it will be missing a case. And you might think, well, that's so what? You just add the case, and right, you can just add the case, and it will also compile. But the good thing is that you can skip this. You can make it structure it in a way that the interpreters don't break. So and why that is useful is because the usefulness I will get to you in a minute in the practical section. Okay. So I won't show you why it breaks because it won't actually break. It will just show an error, a warning, but the warning should be errors basically. And okay, let's get to the final part, which is final as in not the last one, but the final encoding part. So we define an algebra, which is in Scala encoded as a trait over the type A. So it can be any data type which implements these 4 things. Then it can act like you can sum on it. So it can be integers, strings, lists, whatever you name it. So in mathematics, it can there are these abstract ways of saying things, and all the examples you have to think of yourself. So it can be basically anything as long as it has this structure. Isn't that interesting? Okay, so and then we define interpreters for it. So that in this case, for us, that means writing implementations of this trait for some data type. And so we write this. But first, let's look at the way we write code with this trait. So this natural, I think, way of structuring this code for reading would be this. So we have the interpreter, which gives us these 4 methods and returns our data type. And it's parameterized over any A. So as long as we have an interpreter, we can make an A, which whatever thing it is, with this structure. So again, this is the notation that is rewritten, but represents the same expression. And we will get basically something that amounts to this, like abstractly. Right? Good. And with the like changeable meanings of the pluses, minuses, and the numbers. Great. So and then we have to actually implement this trait. Otherwise, we can't actually make any A's. And we make a new trait. Set this A to integer, and then we have just to implement all these methods.
Excuse me. Can you explain why the previous implementation was breaking on multiplication? I don't understand it.
Yes. It was breaking. Well, it would actually just make a warning, but usually it is the case that in all products in evolution, warnings are treated as errors, which they should be, because otherwise, if you make a program that has like unhandled cases, if it will encounter them, you'll break the program. It will just stop. So then that means you get a call at night that your game is not running or.
So the problem is
everything's
that
bad. So
matching is not exclusive. So you mean this, yes?
yes. Mm-hmm.
Okay. So yes, understand. Thank you.
So yeah, if we have not commented these out, then and we don't want to, like we can do it in a way that we don't need to. So again, we make an abstract expression right here. Then we make concrete instances to have concrete ways of making the data that consists of these expressions. We make two different ways, and then we have. I will now scroll, so I will confuse you, but keep this in mind. So in the end, the final version, we print out the integer version and the string version. So if we run this again, we get, why does it say -4? Oh, it's a different one. This one says the same thing, 9, and then pretty printed. And so far, there actually is no development. We just wrote it in a different way. So what? The good thing is now we can add a different way to combine the values, which is this, without breaking these two. So if we comment out this line and say they don't break, well, these refer to the multiplication expressions, but these two don't break. So that is the cool thing about we basically solved the expression problem. Great. So yeah, if we had multiplication expressions, which are again on some data type A and B, we don't even have to refer to the fact that there are also expressions of arithmetic, well, summation, negation, and constants. We don't even have to do that. We just add this, and we can interpret as an integer for integers, for strings, and then we can make we can mix them both together and make more expressions. So that solves basically the expression problem, and I hope by now you have at least some sense of what that is. So final with multiplication, this example, this should be this. It will be printed. We give it both interpreters for strings and for expressions. So you can see that there is more code, like it's separated. So we have to have both instances, and like the separation gives us the freedom that doesn't break the code. So if you're like if you're keeping track of things, then to get this freedom, we have to make separate things. So I think I hope that make this somewhat intuitive to you that we have now two interpreters.
So we're just composing our interpreters together.
Yes, correct. Okay, let's see them. So yeah, this. I don't know. I'm not good at counting, so I assume this is correct. Well, yeah, that is correct. Okay, so that is the first part. Very good. Numbers, very boring. What do we need the numbers for? Actually, I won't tell you. I won't switch away from numbers just yet. There are two parts to the name of the paper. It's called, well, actually three, but the first one is typed, which we'll get to as well. I explained the final part to you. Now I'll explain the tagless part. Actually, I won't, but it will be sort of related. Okay, so actually, no, this is actually about being typed. I'm very sorry. This should say typed anyhow. Okay, what our expressions? All of our expressions in this example consisted of numbers. It's all numbers. So they're the one type. Whatever it is we're making, it's going to be a number. So if we have a constant, it's a number. If you negate it, it's again a number. If you sum it or multiply, it's still a number. So they all can be represented by the same time, which is expression. Well, that's very nice. But what if you make, again, remember that we're thinking about data, but we're interpreting it in a way that we're actually describing code. So if we talk about code, then data should also include all of the ways to describe code. So we can just talk about the code analogy, and it should work for all the cases of data. Well, the data can represent also something else, but it must always be able to represent data. This is like a minor point, but it's kind of, it's important. Okay, so, and at this point, we have to make sure that the type is right. And to exemplify this, I have created two more things. I have this expression which internally holds an A. So and it holds a Boolean inside of it. And then there's a single Boolean expression that also contains two Boolean expressions. Great. But we also have integers. So we can make an integer and it will make an expression of integers. And so if we want to negate it, we have to use an integer just in the same way. If we want to make an OR, we have to make it from two Boolean expressions. So it will allow us to make this all typed. So you can't make malformed expressions. Malformed. There is an example here which I will uncomment because it will show up as breaking. Right? I hope so. Yeah, it highlights it. Very good. That's what we wanted to avoid, to make only valid expressions. Very good. I hope this is roughly clear. Then we can also make the expressions again. We have two expressions. The bad one is failing, and we can interpret it in two ways. Actually get the numbers or marbles or whatever you think of. Like, remember, I'm just using two examples, but that's actually with however many examples you want. So you could have like 1,000 of these interpreters. And if you structure them in this way, you will break them once you add this expression. So I think it's in programming always, and in mathematics makes gives you intuition when you think about, instead of like 3 things, you think about 1,000 things, and that shows you where the edge cases are. So yeah, these all is well and good. These work. I can try them out for you or not. So this is the Tagless one. Tagless is number 126. It is this one, right? Should be this one, yeah. So you can, where's the Boolean expression? Have I not printed it? I don't think I have. Work. Yeah, we get true, or in the same way, but interpreted as a string. We get the code out, which is like kind of cool, isn't it? That we can get the code out, and you can get the number or the numbers code, or whichever interpretation you want to have. And let's break it again. We uncomment this. We should have some movements. All goes well. Great. It's broken. That's that. We're done with this code. Bye. So final. Oh no, it is tagless, right? So this is tagless final. And the point is that the research paper showed that it can also be solved by tagging. So adding like some value that you can check out at runtime that it represents the correct expression. The problem is that why I'm not showing you this. It doesn't like, it's a good motivation for structuring it this way, but this is clear enough to me that I don't even want you to take a look and bother your brain with looking at the wrong way to solve a problem. For me, it's interesting, and for someone who's researching it, it's obviously interesting. I'm not sure it's so interesting for you when you see it for the first time. You haven't even read the research paper. Probably don't want to, but I do encourage it. And come at me with questions if you're interested. So now this is what the initial encoding once again, and it's initial because we're storing the data. We actually have precise ways to make these expressions out of data constructors. And instead, we'll do the same thing again. We'll make functions that represent creating something that has the same structure on any data type. And this time, instead of numbers, we have like both numbers and booleans. So we have to have the types, and that is what used to be the tag, but now it's tagless. Now it has the type actually inside of the data type here as a whole. So that is the parametric polymorphism you had from other lectures. If you saw parametric polymorphism for the first time in that lecture, I'm not sure how easy it is to follow, but we'll have some practical examples which may be a bit more simple, and you don't have to think about like the expression problem so much and all about this mathematical jazz. Okay, so we make the arithmetic expressions, and it will make ints. Great. That is separate. Where's our expression? Now move it up there. So we have some data type which has internally something, and it has the expression arithmetic bound on it, which means that we have to have this trait available, and in this function it has to be supplied. So this is basically an argument, it's just written in a way that is more concise and so on. Then we extract this interpreter. This is like, I can explain this if you would like me to. And we can write the same expression again. And do we need this? We need this, yeah. So we have to interpret it to make sure that it works. We can do it with we have to have some data type to interpret what data does eventually have to be created to interpret this expression. So we use the data type expr, which internally holds just the same thing. So it's just a wrapper. So basically, we could almost do without it. We could just have types, but it's a bit hard immediately to explain why we need this. But all right, because it has to fit the same shape to also allow different interpretations. Okay. Because there has to be some data type there in the first place. I hope I didn't confuse you. Okay, when we can interpret it as an int, we store the int in the expression, we get the expression of int, and so on. We've been through this. I hope this makes sense. Okay, and so we interpret it as an integer. We can also interpret it as a string. So we use the expr show. Let's move here. More related. It's example rather than this. And we have some data, it has some tag which notifies what is inside of the expression, but actually we don't even use it. But it will work magically. Like there's no reason for it to break, so it will work. And so we're saying like it has ints inside, but we really store strings. And so we satisfy this algebraic structure, and we get numbers shown to us. And obviously, if I can run this, it should be this, yeah, expr and expr show. Very good. Now we add the algebra to talk about booleans inside of this data type. And so expression is here, and we'll move it there. So this represents false or true, just in the renamed notation, which again notifies the same expression. We have, this time I used a different syntax. So here I had f, which had the expression bound on the f, which had the bound expression arithmetic. This is the same thing. So we have the expert, and it has, we are supplied with the bound, with something that satisfies the expression, which is basically, what I'm trying to say, I'm being a bit tongue-tied. These represent the same thing. So in this case, we have an f, which has the expression arithmetic, and this is the same thing, but instead it's Boolean expressions satisfied by the expert. Great. Same way to say the same thing. We import all the methods, so we don't have to write prefixes, and we get this. So that's, I don't think you're quite gonna be quite interested in. This is not surprising yet, I don't think, at least. But okay, we can interpret these booleans. I don't have a a way to make strings out of this, but I can make the booleans themselves at least. Yeah, and so I store them in the same expr, which is this one, and it will make booleans for me. And the thing is that if we remove any of the boolean part, or add more things that can live inside of our data type, it won't break the old interpreters. So basically, we are parameterizing over any data type that has the structure, and that gives us freedom to write better code if we know how to leverage this. And that is like, if I had only shown you this, I don't think you would immediately know how to leverage this, but that's why I have the third piece of code that is like the practical examples, and we'll get to them immediately. I had some lecture notes which I wanted to mention, but I skimmed over them immediately, I think, because if you're yeah, I could show you how what this actually means, I guess, but my details also show it here. And yeah, this is like technical details about how it works. I guess that would be good to explain in a moment. Oh, and obviously, if you can make a practical programming language that lives inside of the Scala type system and behaves correctly, if we add another algebra like trait that has the expressions to combine the booleans and the numbers. So we haven't done that because like we just keep using the same principles to do something else, but the point is not to make a programming language yet, but just to show that we can abstract over data types that have some internal structure. That structure is called an algebra. Okay, moving on. If you would like me, before I move on to the next thing, if you would like me to explain the difference between this syntax and this way of expressing it, do notify me at some point if I have forgotten, but I won't talk about it just yet. I have two exercises which we could do right now, or you can do it at home, or I can show how to do them and then you can do them again, because I don't think you will immediately, unless you're like you've been doing this for a while and you already know everything, and actually I didn't even need my lecture. You won't be able to, I would wager, you won't be able to recreate them immediately. So I have one so this is the practical part. You suffered through the theory. I hope it wasn't too boring. I hope some of my enthusiasm comes across. Let's do something practical. So this is a contrived example where we have some, let's imagine that there exist users, and we have a user case class, and then we have a wait to get the users. So this in reality would probably either use the disk or the network connection to connect to some database or use memory. So wherever the data is, there are multiple ways to get it, and we can talk about all the ways to get them in with the same app. So we care that there is some data type that gives us the structure of getting users. So this would be that. So basically, of all the data types that also are actually doing the computer doing some very complicated things, we abstract over all of them and say that it has to be able to get users. And obviously the simplest way is just to make them up on the spot, which is what we are doing here. We can find the user and it will just give us a user. It will make it up by so the user has an ID and an age. It will make up the age by hashing the ID. So this is that. And then what we could try to do is make a function that finds the users that have matching birthdays. Oh, sorry, ages. And age match. Wait. Full of bugs, my presentation. I'm very sorry. Right, and just to clarify what this is, and this is there. These are supposedly scary words. Some people think, though they can be certainly. This function is we're parameterizing over effects and have the applicative thing, which basically allows us to put the values in our data type. So it has the structure that allows to create values in the data type we are extracting over, just like that. We just say, let's insert this value into our data type, and it allows us to. That is what the applicative does. It does also other things, but this is one of the things. So we can say applicative give us a pure value that is inside of this data type we're extracting over. So this can be like practically get a number from the database, which is like over network or anything, or just there's no actual computation that you can't keep a track over. So it's just pure values, and yeah, that is what this is. This allows us to make a thing. So we can basically, it gives us an instance of find user, and then we could write code that satisfies, that basically uses this this algebra to give us some code. And the cool thing is that if we take a look at this this code, you can see that it is abstracted over any app. So long as we have a find user instance of app, this means that if we set app to something that is called the identity, basically data type that if it holds some A, then it only has an A inside of it, which is to say we can set it app to something that will not do any actual work that we can't keep track of. So those are called like the effects, like calling the database, or like we can control everything. So this shows that this method is very dumb. Like it won't, you know that if here it says identity, then you know that it can't connect to network or anything. So you can because of these bounds on F, you can infer that it's not doing a lot of work. So when you have to read less code because you're not looking for database calls in this, or like memory calls, or like lookups to memory or something like that. And this is one thing which we can implement. And there's another thing which is give us the largest of 3. So again, we have some effect type, and which also allows us to get a random number. This is our algebra, or just a trait. You cannot say, you don't have to say algebra. It might actually confuse people, but technically you can do it that way. and then it has to get the largest of 3. So we can do one of these two or both, or you can give me questions about the syntax of these things, about how it all works, and tell me whether this presentation sucked or not. This is the interactive part where you have to speak up.
For me, it's clear.
Great.
You totally lost me today, sorry.
Well, it involved a bit of mathematics, so like it's a bit tricky, yeah. But I there was a possibility to interrupt me and ask me questions, but I guess that's fast because like you got lost. But still, if there's something you would like me to clarify, and also there's a way to like continue without actually thinking about the math too much, which is just looking at the practical examples. Well, this is what it's used for mostly in like in our company, in most companies. Well, you have other uses. The number use is actually real for both making numbers like just be computed or making their printed values. That is also being used not in Scala but in a different language. Yeah. So if you don't know anything, like let's look at the schedule for your. I'm not saying this schedule proves that you know everything that has been talked about, but effects come later. So we talked about this technique of abstracting over things that implement some structure, and this is in this lecture. It's actually the way where it's most used because it's effectful code that changes things around you, like in the memory or in the disk, or makes calls or prints something. That's the code that's most difficult to handle because it can make unpredictable combinations and you don't have full control. So yeah, this code is all with effects basically. And I checked the previous speaker on this topic, and he had a lot of effects. And I thought, well, I wasn't sure that they would be immediately clear. So that's why I did this very briefly. Questions about the syntax, or maybe you want to see one of the examples being done? Anything?
Rentis, could you please explain one more time what are benefits or proofs that we gain from switching to tagless final from previous examples, from previous files? Is except of what we now can specify more methods in our trade, and it will not break implementation of our methods what we combine.
I see where you might have lost the connection. So this
I'm sorry.
About what? You have nothing to be sorry about.
I have lost connection.
No, that's not your fault. So the thing we gain is we can talk. This allows us to talk about more data types than we would normally. So if we would write this method the normal way, or like this one, I still won't implement it, but it will. So there is no bound. We've now set the f to a precise thing, which is IO. So if we have IO means do anything. You can make it. You can look up information from the hard drive. You can make network calls. You can, I don't know, take a look at the screen, whatever. So this gives us a lot of power. And when you see this, like you can be a bit skeptical because, like, comparatively. So we have this find user, okay, but what if it actually? So we know that it only has a single method. What if it does something like this? Find user, and then it's, I don't know, this one code won't work, but it gives us the user, and then it also says like print user found ID 1, something like that. Or also it I don't know, someone's what, like this is an actual example, like it printing stuff out, or like obviously this is not about usually our code is somewhat trusted, so it's not like there's going to be something very malicious in there, but still, you know that it's as dumb as this method. It can only do this. It's making combinations in the expression that is the resulting expression. It can only make things that have to do with this, basically, and also monadic expressions. So it can change the user data that it gets, but it won't do much else. So because this is set to whatever, so it can't actually do more than, it can do less than it would normally do if it didn't use this technique. And that is the thing that allows us to do, like,
Okay.
encoding in Tagless final allows us to give this gives us more knowledge.
Freedom to choose in what context we write our implementation.
Yeah, and that constricts the function to be a dumber function. It can't do anything. Yeah, it gives the function freedom, and it also constricts it.
Yeah, but maybe it's a stupid question, but why can't we use higher candidate types and and this form of abstractions, or it?
If we can, then you have to show me how.
Okay,
There is a
don't know.
There is a higher candidate type here, and so basically we are using it, in fact. But yeah, this is the way to do it. Like, we are indeed using higher candidate types, and though we don't necessarily have to. This and the previous examples, you could have it could just return A. So the technique does not actually require you to have high candidate types. Yeah, but in this case, when we're working with types that internally have like some parameters that have to be like specified, so it returns the user. So they combine only in the specific ways.
Okay. Yeah, I got it.
Yeah.
Thank you so much.
Do you know what this colon means? And
Sorry, could you repeat the question?
So do you know what technically this colon applicative means? Like, what does this colon represent? Like, it's a bound. F.
We are bounding our context of F to applicative.
It means we should have an implicit value that has two methods, pure and app.
Yes, that is correct. I could show you, like, yeah, if someone's interested in seeing like how the implicit comes into play there, I guess that can happen. But this is, I've said the most interesting things already, and all that's left to do is for either us or you to implement these methods. Do I have this? I think it compiles, right? It does. Oh, push! It's actually not in the Scala Bootcamp. Where's it gonna put? The repository, it's in my private repository because I didn't push it yet, but it's here. If someone is interested in taking a look at the examples. Ah. Any suggestions on how we continue? Would you like me to show you the implementation of one of the functions that we could? Let's do largest of 3. And I also can explain like another practical, like how it practically works. I'm a bit unsure of what the percentage of people lost and people very interested and focused and people like who already know this, what the percentages are. This would be talking to the percentage that is very focused, interesting, and right exactly able to consume this content effectively. So, but I will talk to you through this practical example very quickly. It also involves effect types basically, but we don't even have to think about that too much. You just have to know that there's some data type that allows us to get a random number. So the f, yeah, it has to be able to make up random numbers, and it can also pop things into existence. So, and we have also made a trait which gives us a random number in from 0 to I, not including I. And so when you read this signature of this function, like this, the type.
Excuse me, honestly, it's not clear what should we actually implement. For example, line 57.
I guess, yeah, that's a fair point. So we will have some f with which we can make random numbers. And the largest of three of those numbers should be returned. Does that make sense?
We need to generate 3 random numbers and return the maximum of them. That's right.
Yes. Yeah. And we know because of these bounds that we can only make make up values of new numbers within this code, and we can make new random numbers, but it won't do any like this calls. It won't try to break our computer. It won't try to make any sounds. So it's pretty limited in what this function can do. It can obviously run code forever. It can run in a loop that computes something forever, or make a very long computation of like lists or something and then discard it. It can also do that, but still
this one
we have limits.
Quite simple. It's like the first step, we should just generate 3 random numbers. It's like we should write something like f implicitly f no, implicitly basic random dot next int bounded. Maybe we should choose some number ourselves, like 10 maybe.
Let's take 100.
Yes, and it will return f of int, and we can use 4 comprehensions to
and we can't actually do this. Okay, how about we give it?
We cannot use 4 comprehensions, but we can use applicative map n.
Yeah, we can use that then. That's what I did last time. That's why it worked. Okay, this is one of the examples.
It's because these 3 numbers are independent from each other.
Yes,
correct. We don't need monad.
Yeah, so this is the one way to solve it. If you just make it into a monad.
We can write
And-
tuple find, and then map n, and then something else.
Yeah. Or there's another version which I wrote last time before this lecture. It could be like a list of 3 things, whatever they are. I hope I'm gonna remember correctly. So we ignore those things and we make let's remove one back to applicative. And we call the same thing. We should be able to get a list, an F list of. So I will add parentheses. So it gives us some information about what we're getting. Missing that. So this should be a list, F list of things. And map that to max value. And it doesn't work. How did it work the last time? What did I put there? How is it possible? Now it works.
We probably need the find implicit or function. We can call it function on the line 59.
We need a more relaxed bounds.
I mean, we can use the function find on the line 59.
Function. Could you spell that out for me?
In your code editor, you created a value called FINT, line 59 find, this one. Can we try another way to do this?
We can, yeah. But basically, yeah, this is one of the ways to do it. So let's comment that out. And this one, let's comment this out.
Yeah, I mean, the third one, can we try it like create a tuple with 3 values find, a tuple of values find, then map n, or something like this. Okay, map n, and then we can use a function that accepts 3 numbers and returns their maximum. I believe that this should work.
Yeah, this also works. So there are a bunch of ways to do it, but you know that all of them will be pretty restricted in what they are actually capable of doing. And this marks the beginning of the 1 hour and 30 minutes almost. So I think that might be quite enough for one day of lectures. I know my brain would certainly be fried if I saw this for the first time. So any other questions? Or comments about what
could you tell? Yeah, could you tell me, please, if we may read off implicitly in this particular method? Could we implement something without implicitly, without using it?
Yes. So what this really means, it says that we have to have the applicative interface with the F available and the basic random interface available. So we can write that it has function arguments, I can say that it must require so op of f would be applicative of f, and in a basic random of f would be this. And so this is the same way of saying it, but with the implicit. So they have to be found when this function is being called, they have to be found. So if we remove this, this is the same way. So as writing this, then we don't actually have to write the implicitly. Or we can, but we can also just say basic random, or we can, since they're implicit, we can. So this is the same thing as this, but in this case we have the names available, and this time we didn't have them. They were. We can find them, but we don't have assigned names to those data. And if you save this now, then it breaks.
Proceed.
Oh, well, we still have to have some f that has a time parameter. That still has to be defined as polymorphic so that we can use it. What's next? I screw something up. BR, there's no BR, there's BRF. And now it should work. So that's that. Just in the case where we did this. So we have the interpreter available, or we can say there is a bound on it, and then I found it with the implicitly. So the implicits give us a way to find something that exists like in the context without actually talking about it. We don't have to mark explicit ways where we found it from. We just know that it's available and it has to be found. And if it won't be able to be found, then it will be a compilation error.
So we have implicitly at 76 and 77 line 76, 77, 70.
Yeah. What about them?
So
this will find the same thing. Same thing. I'm just showing that both of these will work. Obviously, you would only choose one. You can rename them. Yeah, but you can use both because it's implicit, but it also has a name. So sometimes you do this just so you don't have to talk about it implicitly everywhere. But yeah, this is a two-way of saying things. So
we don't need APF variable at 59 string. We haven't used it in the implementation.
I haven't used it. Technically, I'm using this instance in this line, map n, but we don't actually need a name. We can just put it back. Oops, where did I go? So this is one way of doing it. Yeah, and then the other way would be to say map n gets a tuple. So this map n is no longer needed. And it should have a second argument, which didn't. That's wrong. Applicative of f. So it work. Well, the method should be available somewhere there, but we can change it to like app3, I think. That should also be able to be changed, but right now I don't want to bore you with how exactly.
Okay. So, in your opinion, what approach is better, or maybe to use implicitly or to use implicits in signature of method, like BRF and APF, something like that? Just interesting.
first write whichever one works. Oh, there's two implicits. First, you write whichever one works, and then you learn all of them, and then you write the one that is shortest. So first of all, you have to have some code, then you make it. Well, then ideally you make it look better, but you don't know. So you don't know how to. So first you have some code, then you learn all the ways to make it different, and then you pick the best one. As always in engineering. But
Okay.
honestly, in work related projects, you can come up with anything and you send it to colleagues, and then they say it sucks, and they show you how to do it correctly. They'll help you improve, and it's fine as long as you have some code that works, I think.
So I just wondering why approach with implicitly word like your first implementation is used. So it's more readable or shorter than that approach that we currently now see on screen.
This looks better for creating integers, and this looks better for because I get the map n, which is from like methods that use the implicits. So this is the way I would actually probably write it. Instead of, however, I would call it just random. Legal code. It should look something like this. Well, or any of the other choices.
Okay, so personally, I think that it's more readable. It's only my thought. So thank you so much for explanation.
Yeah. Well, the readability is a thing you can talk a bit about. I'm very actually not very strict. As long as it's not too much code, you can write all sorts of things because it's usually understandable anyway. Yeah, it's always a debate about readability. Okay. Any other last questions before we finish? What did I have in the presentation? I had some last slides. Yeah, so it gives us the ability to abstract over effect types, and then because of that we get to see what precisely it uses instead of like being able to do anything. And also we can like test. This is something I would have liked to add an example for, but I forgot. But basically you can, well, no, I kind of did, but I didn't drive the point fully, but we're still like, it was a long lecture already, so we'll have to skip it. But you can like test your units with different effect types that are still not, that still can't do anything, like they're very constrained. But that's definitely for another thing. Oh, and then this link shows us that it's in a different language, but this way of saving, this way of describing numbers is truly used in the wild, which is in Haskell. Like this is a trait which is abstracts over some a, and so the plus is just about any a, so it can indeed be string or anything else you'd like. So that is a cool thing. And then the references are these. This is the lecture notes that I used, which are like quite extensible, and they're a bit academic. So even I'm not an academic myself, but I can follow most of it. But it still refers to like different things that are not clear to me, but I could read it somewhat, and it has a lot of different examples on how to like use this way of writing code to completion. And there's also this paper which I read before that one, just to prepare me for reading these lecture notes, which is very interesting about how you can represent things in different ways and still come up with the same thing. And then I read some Reddit thread that just confirmed me that I know something that they're talking about. I think this should be it roughly. The only thing, questions? Am I hearing someone speak?
Excuse me, a bootcamp question. Do we have a homework for this lecture?
I understand that the homeworks you had were like formalized, and then you could be like, if not graded, then someone could see you've done them or not. I haven't structured them in this way, so the homeworks are only for yourselves to like try implement these methods, these find age match and largest of 3, if you could do it again. But it might be difficult or it might be not. If you want to challenge yourself, I welcome you to. And maybe like,
so may I ask a question about this find age find match age function? What should concretely here we do? Should we how we have no input parameters in this function like numbers, or we do not have random context bound? How can we get some
technically? Yeah, technically you can kind of put it together, but if I would have to write it precisely, then assume that we have 100 users in database from like
we can iterate from 1 to 100, right?
Yeah, and then we have this trait, which has a concrete implementation of, which is given here. And then if you run the main of this file, then it will execute this thing, and it should be able, it should check whether there is a match with, if there are 2 users with the same age. Yeah. And it's in my fork. It's not yet merged, so that's what it should do. Maybe this is. Okay, anything else? So basically no homework unless you want to challenge yourself.
I'll give it a try. Thank you.
Beautiful. That's it then? I guess so. Thank you for listening.
Thank you, Raitis, too.
Thank you. Thank you so much.
Thank you.
Thank you. Bye.
Bye.
Ciao.